in your book in the topic of the motional EMF, such like diagram will be present. So, as the name motional EMF indicate that the EMF which is induced due to the motion of the conductor in the external magnetic field. So here is the same scenario. We have this conductor and which is present, which is moving with velocity v in the external magnetic field. In this case, these cross symbols represent the external magnetic field, which is actually pointing towards your pointing from you towards your screen. So this is the direction of external magnetic field, and here the conductor uh, is present here is moving from left side towards the right side with velocity v. If the conductor is moving with velocity v in external magnetic field, and induced EMF will be developed inside that conductor. So here we have the conductor which is labeled here as a blue color, and this conductor is moving with velocity v in external magnetic field. And we know that when the conductor is moving in the external magnetic field, the current, the force F will be exerted on the electrons, the free electrons present inside that conductor. So the direction of that force exertion on the electron is given by this right hand rule. So here your thumb represent the direction of the motion of the conductor in the external magnetic field, and your four fingers represent the direction of the external magnetic field. Here in this case, that external magnetic field is from you towards your screen, and your palm represent the direction of the force exert on the positive charge. Okay, so here from this rules, we can say that the force exert on the electrons present in the conductor in this direction. So due to which these positive charge is moving towards the upper side of the conductor, and the negative charges leave behind that positive charges in the other end of the conductor. So that same moving conductor present here in this diagram, and the lower side of that conductor is labeled as a negative charge, and the upper side of that conductor is labeled as a positive charge. And this moving conductor is actually rolling on these two conductors, and when the positive side of this conductor is in contact with this conductor, the charges, the current will flow, which is called the conventional current, from this positive side and will complete this circle. And similarly, this conductor is moving, and due to their motion, the change in the area is occurred. The original area was this, and when the conductor is moved from this position toward this position, so the area has increased. So this change in the area is given by the change in the width, and which is actually called del x. And this del x is actually, let's say this is x1, the original position, and this is the final position x2, and the change in the width is given by the del x. Okay, the change in this side is given by del x is equal to x2 minus x1. Okay, so del x multiply this length, which is labeled here. So this del x multiply this length is called the change in the area. So Due to the motion of this conductor in the external magnetic field, the change in this area enclosed by this circuit has occurred. So the change in the area leads to the change in the magnetic flux, and as we know that when the change occur in the magnetic flux, and induced EMF will produce, and that induced EMF in this case due to a motion of this conductor is called the motional EMF. According to the Faraday law, the induced EMF is given by N del phi divided by del t. So here this del phi is actually the change in magnetic flux, and in this case that change in magnetic flux is originated due to the change in the area. So let's say this is equation 1, and we know the equation of the magnetic flux, and magnetic flux is actually the B A cos of theta. So the change in magnetic flux is given by del phi, which is equal to this B is actually the constant which we call the uniform magnetic field, and in this case it is from you towards your screen, and here this B is uniform and only change occur in this area. Here this first the area was this, and it has increased to this position. Okay, this area has increased, and in this case the change is occur only in this area, and we put that del with this an into cos of theta. This theta is actually the angle between the external magnetic field and the area a. So here the area is present here. So this is actually the area, and we know that the direction of the area is always perpendicular to this area. So the direction is actually inwards to the screen, and the external magnetic field is also inwards to the screen. So therefore the theta here is 0. So we can put the cos theta, the value of theta here is 0, and then it will become this. So the change in flux is equal to B del A cos of 0, and cos of 0 is equal to 1, so it will become B del A. So this is the change in magnetic flux, and if we put this here in equation 1, the electromotive force is equal to N, and instead of this change in magnetic flux we will put this B del A. B del A, and divided by this change in the time. So the change in the time, and this change in the area is equal to L into del X, and this del X as we saw here is the x2 minus x1. So instead of this del A we will put this value, and due to which that this equation become, so electromotive force is equal to N B, and instead of this del A we will put L del X, okay, and divided by del T. Okay, so here this del X divided by del T give us the velocity. So it become N B L, and this del X by del T is equal to V. So therefore we write V instead of that. And here the number of the turns in this in this is 1, so this become B L V. So here this current I from the Ohm law is given by I is equal to V is equal to IR. So this is equal to electromotive force divided by R. So the electromotive force here is given by BLV divided by this R. So this is the relation for the current. This is equation 2 and this is equation 3. Due to this velocity in the external magnetic field, some force will exert on this conductor, and which is given by this relation, and which is equal to I, L, and B. The power produced in this case is given by P is equal to work done per unit time, and work done is actually the F dot S divided by T, and which is equal to F is uh, cos of theta and divided by T, and here cos of theta is equal to cos of 0 is equal to 1, so it is equal to F S by T, and S is actually the distance covered and T is the time. So the distance covered per unit time is called velocity, so it becomes F and V. Okay, so the power is equal to FV. So put the value of F and V here. So P, this power is equal to F, and F is given by I, L, and B, and similarly V. So we will multiply that V velocity. Okay, instead of this I, we will put this value, and this become B L V, okay, divided by R, which is present here, and multiply this with this L, okay, with this L, and this multiply with the B, okay, and we have this V, okay. So the power produced in this case is equal to B square. This B and this B will multiply, this become B square, and this L and L will multiply, it become L square, and similarly V square divided by R. So from here we conclude that the power is actually directly proportional to these three, which is actually the external magnetic field, the length of the conductor, and velocity, and this power is actually inversely proportional to the resistance of the conductor. So if P, so here this power is directly proportional to B square. This B is actually the external magnetic field. If we increase the external magnetic field, the more force will exert on this conductor, and due to which we know that this power is directly proportional to this F. Okay, so if this F has increased, then the power will be increased. Therefore we conclude here that the power is directly proportional to this B square. And similarly, if we increase the length of the conductor, the magnetic field around this conductor will be more, and when the become more, so then more force will exert on that conductor, and this and that force is directly proportional to the power. So therefore this P is directly proportional to this L square. Okay, and similarly if we increase the velocity of this conductor, due to which the more current will be induced, and that increase in the current will produce the more magnetic field around itself, and when the magnetic field is more, and due to the interaction of that magnetic field with the external magnetic field, the more force will exert on this conductor, and when this force has increased, the power will be increased. Therefore we say that P is directly proportional to V square. And similarly, this P is inversely proportional to the resistance of this conductor. If the resistance is increased, then less current will be flowing in that conductor. Okay, so if the current is less, then less magnetic field will produce around this conductor, so their interaction with the external magnetic field will be lesser, and due to which less force mean the small force will exert on this conductor, and when this force is less, okay, and that is directly proportional to this power, due to which this power will be less. And so if we increase the resistance, then the power will be less. So this therefore we therefore we conclude this power is inversely proportional to the resistance of this conductor. So this was about the in-depth intuition of the motional EMF, and I hope you got my point. And that's it, guys. And thanks for watching.